The separation of water alcohol mixtures by distillation is often made difficult due to formation of azeotropes. And in industrial practice, purified alcohols that are demanded by industry requires the use of entrainers such as cyclohexane or benzene in order to alter the vapor-liquid equilibrium. But the use of such entrainers increases the energy consumption, and there is a need for more energy efficient ways to separate water alcohol mixtures than use of azeotropic or extractive distillation. One solution is to use a hybrid of distillation with membrane separations. I illustrate here a schematic for separation of mixtures of ethanol and water that consists of a hybrid of a distillation column that is linked with a membrane permeation unit. The top product from the distillation column, which is rich in ethanol, say 95% by weight of ethanol and 5% by weight of water, that corresponds roughly with the azeotrope composition, is separated in a membrane pervaporation unit that selectively removes the water from the feed mixture, and the retentate contains high purity ethanol, and the permeate is recycled back to the distillation column. The membrane layer could be a zeolite, such as LTA4A zeolite, that consists of cages separated by narrow windows of an aperture size of 4 angstrom. The windows are partially blocked by extra framework cations, and the permeation of water across the membrane is aided by 2 separate factors, and that is the diffusion selectivity that favors the smaller water molecule, and what is less well known is that the absorption selectivity is also in favor of water, and that is what I wish to highlight in this presentation. For background information and theory of the material I will present today, please refer to my paper co-authored with Jasper van Baarten that is available online in Journal of Membrane Science 2024. The membrane science paper co-authored with Jasper van Baarten describes configurational bias Monte Carlo simulations of water alcohol mixtures to investigate the absorption of water alcohol mixtures in 5 different host materials. DDR zeolite that consists of cages of 280 cubic angstrom that are separated from adjacent cages by window apertures approximately 3.7 angstrom and 4.4 angstrom. Also considered is Shabasite zeolite that consists of cages slightly larger in size, 316 cubic angstrom, separated by 3.8 angstrom, 4.2 angstrom apertures. LTA4A zeolite that consists of cages of 743 cubic angstrom separated by windows of approximately 4 angstrom. Fungicide zeolite that consists of larger cages of 786 cubic angstrom separated by larger windows of 7.3 angstrom. And the fifth host material used as membrane layers is ZIF that consists of cages of diameter 11.6 angstrom, and the windows are flexible with an aperture size of 3.3 angstrom. Our study uses configurational bias Monte Carlo simulations to investigate adsorption equilibrium of water alcohol mixtures, and also molecular dynamic simulations of diffusivities of guest molecules within these 5 host membrane materials. For adsorption of mixtures of water, ethanol, water, methanol, methanol, ethanol in microporous crystalline materials, we have the phenomena of molecular clustering due to formation of hydrogen bonding, and the ideal adsorbed solution theory will fail to provide a quantitative description of mixture adsorption equilibrium. In bulk fluid mixtures, the activity coefficients depend on the mixture compositions, say mole fractions xi. The situation is different for activity coefficients in the adsorbed phase within microporous materials. In this case, the activity coefficients of any component I depend not only on the adsorbed phase mole fraction xi, but also on the pore occupancy. We must satisfy 2 sets of limiting conditions. As the adsorbed phase mole fractions of any component I tends to unity, the activity coefficient of that component must tend to unity. Additionally, if the pore occupancy theta, which is related to the surface potential phi by this expression, where Q sat mixture is the saturation capacity of the mixture, this expression for the pore occupancy, as this tends to 0, the activity coefficients for all guest molecules must tend to unity. Before examining water ethanol mixture adsorption in a number of zeolites, let's examine the non-idealities in water ethanol liquid mixtures. I plot here the activity coefficients of water and ethanol indicated by the red line and the blue line respectively as a function of mole fraction of water in the bulk liquid phase mixture x1. As x1 tends to unity, the activity coefficient of water tends to unity. Similarly, as the mole fraction of ethanol tends to unity, the activity coefficient of ethanol in the bulk liquid phase mixture tends to unity. So the limiting conditions that must be satisfied is that as xi tends to unity, gamma I tends to unity. I plot here the Gibbs excess free energy, which is defined as x1 ln gamma 1 plus X2 ln gamma 2. And here are the NRTL equations describing the variation of gamma 1 and gamma 2 with the mole fractions in X1 and X2 in the liquid phase. There are two independent parameters, tau 12 and alpha 12. It's important to note here that the activity coefficients of both water and ethanol exceed unity, and the excess Gibbs free energy divided by RT is a positive number. In my paper with Jasper van Barten published in Fluid Phase Equilibrium, I describe configurational bias Monte Carlo simulation data for absorption of water ethanol mixtures in all silica Chabazite zeolite. 3 different campaigns were conducted for water ethanol mixtures in Chabazite. This is the data for a mixture in which the total fugacities of components 1 and 2 in the bulk fluid phase mixture is 10 kilopascal, and the mole fraction of water in the bulk fluid mixture is varied from 0 to unity. I plot the activity coefficients in the adsorbed phase for water, indicated by the red circles, and ethanol, indicated by the green squares, as a function of mole fraction in the adsorbed phase mixture. The data is determined from the CBMC simulations. In a different set of CBMC simulations, the bulk fluid phase is maintained at a constant composition of mole fraction 0.5 for both water and ethanol, and the total fugacity F1 plus F2 is varied from very low values to values of about 1 megapascal. The data on the activity coefficients for water and ethanol is plotted as a function with surface potential. For further understanding of the concept of the surface potential, that is a proxy for the spreading pressure, I refer you to my paper in Fluid Phase Equilibrium. Watch also my presentation on the real adsorbed solutions area on my YouTube channel. We note that as the surface potential tends to 0, the activity coefficients of both components tend to unity. And a surface potential of 0 corresponds to infinitely dilute components 1 and 2 in the mixture, and the activity coefficients in such cases must be unity for both components. So we must have the limiting scenario as phi tends to 0, gamma I tends to unity for both components. Here are a different set of CBMC data for water ethanol mixtures in which the bulk phase composition is maintained at a mole fraction of 0.05 for water in the bulk phase and 0.95 for ethanol in the bulk phase. The total fugacity F1 plus F2 is varied from very low values to about 1 megapascal. The activity coefficients are plotted as a function of the surface potential, and we note again that as the surface potential tends to 0, the activity coefficients of both components tend to unity. In order to satisfy these limiting conditions, we must introduce a correction factor here in the NRTL model for the activity coefficients and components on 1 and 2. This correction factor is 1 minus exponent of minus c. C is an additional constant that needs to be determined from fitting the CBMC data, and phi, of course, is the surface potential. This correction factor is essentially the pore occupancy. So essentially what this expression says is that as the pore occupancy tends to 0, the activity coefficients must tend to unity for both components. Many models in the literature, I have named these papers in my fluid phase equilibrium paper, ignore this correction factor, and these models are not trustworthy. Let's look at the Gibbs excess free energy for the 3 sets of CBMC data for water ethanol mixture absorption in Shabasite. I plot the 3 CBMC data sets for the excess Gibbs free energy divided by RT, which is given by x1 ln gamma 1 plus x2 ln gamma 2. These may be determined from the CBMC simulations. These are indicated by the red circles, green squares, and the yellow diamonds for the 3 sets of CBMC simulations shown in the foregoing slide. The entire CBMC data set resides on a 3D surface mesh that has been generated using the fitted NRTL parameters with 3 different constants: the parameter C, the parameter tau 12, and the parameter alpha 12. The fitted parameters are provided in my paper. For further background, I also refer you to a number of presentations on the RAST and non-idealities in the mixture absorption on my YouTube channel. Having modeled the activity coefficients for water ethanol mixture absorption in Shabasite, let's examine the water ethanol absorption selectivity in Shabasite. For the 3 different CBMC data sets for water ethanol mixture absorption in Shabasite, I plot the water ethanol absorption selectivity as a function of the surface potential and the mole fraction of water in the bulk fluid phase mixture Y sub 1. The 3 CBMC data sets are shown by the red circles, green squares, and yellow diamonds. It's important to note that the selectivity for water with respect to ethanol varies monotonically as a function of the surface potential and the water in the bulk fluid phase mixture. This characteristic is followed for all binary mixtures investigated in this paper. Watch also my presentation, Does the Absorption Selectivity Vary Monotonically? No maxima in the absorption versus surface potential or absorption versus the bulk fluid phase mixture composition is to be observed and detected. Indeed, if we examine the expression for the adsorption selectivity, this works out as a ratio of the product of the absorption pressure for component 2 times the activity coefficient for component 2 divided by the absorption pressure for component 1 multiplied by the activity coefficient for component 1. And if we use the model for activity coefficient, say the NRTL or the Margulis or the Wilson equation, it is straightforward matter to deduce that the adsorption selectivity does not exhibit maximum as a with respect to either phi or y1, and the variation is monotonous. For a water ethanol mixture adsorption in DDR, configurational Bayes Monte Carlo simulations were carried out for 4 different campaigns, 50-50 mixtures of water and ethanol in which the total fugacities varied from small values up to 1 megapascal, 595 mixtures in which the fugacities varied up to 1 megapascal. The yellow diamonds are the data for water ethanol mixtures at a total fugacity of 10 kilopascal, and the composition in the bulk fluid phase mixture is varied. The inverted yellow triangles are for water ethanol mixtures in which the total fugacity is 1 kilopascal and the mole fraction of water in the bulk fluid mixture is varied from 0 to unity. The 3D plot here is one in which the water ethanol adsorption selectivity is plotted as a function of both surface potential and mole fraction of water in the bulk fluid phase mixture. We note a very important conclusion that emerges here is that for large values of surface potential and small compositions of water in the bulk fluid phase mixture, the adsorption selectivity is in favor of water rather than ethanol. And this is of vital importance for permeation of water ethanol mixtures across pervaporation membranes, because in the hybrid scheme for distillation combined with membrane pervaporation, the mixture which is rich in ethanol and poor in water is sent to a membrane pervaporation unit, and since the mole fraction of water is smaller than, say, typically about 5%, the adsorption selectivity is in favor of water. The diffusion selectivity is also in favor of water. So both adsorption and diffusion serve to produce permeation selectivities that are heavily in favor of water compared to ethanol. DDR is one of the important candidates for use in pervaporation separations. The selectivity reversals that is observed here is caused by entropy effects that favor the adsorption of the smaller guest molecule which in this case is water. Watch also my presentation on entropic separations on my YouTube channel. The CBMC data for water ethanol mixtures in DDR zeolite for the activity coefficients for 3 different campaigns are plotted here. These are analogous to the corresponding data for water ethanol absorption in Chabazite. For a total fugacity of 10 kilopascal, if we vary the mole fraction of water in the bulk of fluid phase mixture, we see that the activity coefficients satisfy the limiting conditions as xi tends to unity. The gamma I of that component tends to unity. For 50-50 mixtures, the activity coefficients in the adsorb phase are plotted here as a function of surface potential. And we note that as the surface potential tends to 0, the activity coefficients of both components tend to unity. This is also true for 595 mixtures of water and ethanol. To properly model these CBMC data sets, we need to properly account for the correction factor 1 minus exponent of minus parameter C times the surface potential, as I have discussed in detail in my paper in fluid phase equilibria. Watch also my presentation on the real adsorbed solution theory on my YouTube channel. For adsorption of water ethanol mixtures in Chabazite, DDR, Faugisite, LTA, ZIF8, the activity coefficients in the adsorb phase mixtures are less than unity for both water and ethanol. This is in sharp contrast to bulk water ethanol liquid mixtures for which the activity coefficients of both components are larger than unity. So never use the NRTL parameters fitted for water ethanol liquid mixtures to estimate the activity coefficients in the adsorb phase mixture. The results would be worthless and also meaningless. For modeling the activity coefficients in the adsorb phase mixture, it is important to incorporate the correction factor 1 minus exponent of minus C times the surface potential, because this correction factor ensures that the correct limiting behavior is observed and obeyed. The water ethanol adsorption selectivity is a monotonous function of both phi and the mole fraction of water in the bulk fluid phase mixture. The adsorption selectivity is in favor of water if the composition in the bulk liquid phase is smaller than 0.05 for water. It is also in favor of water for high values of the surface potential, because at poor saturation conditions, the mixture adsorption equilibrium is dominated by entropy effects. This is an important aspect of membrane pervaporation, because for removal of water selectively from water ethanol mixtures with small amounts of water, is the adsorption selectivity is in favor of water, The diffusion selectivity is in favor of water because due to the smaller size of the water molecules with respect to ethanol, and therefore in membrane pervaporation using, say, DDR, Chabazite, LTA4A zeolite, and ZIF8, both adsorption and diffusion complement each other.